Okay, so looking at the layer 2 802.1q, which is the trunking class of service header. So here's our Ethernet frame. Here's the data payload. And within the 802.1q header, we've got our tag for our 802.1p bits. Now this is the 802.1q tag. It contains the VLAN ID, but it also contains these 3 bits used for priority, the 802.1p priority bits. Okay, so the 802.1p priority user field, also called the class of service, has different types of traffic, and they're assigned these different values. Now, cost 6 and 7, the 2 top ones, are reserved for network use. So 0, which is the default, is just best effort data. 1 is typically used for bulk data, although you'll see that we might choose to change that. 2, used for critical data, and these are just generic tags. We'll actually unpack what we mean by these tags or what we're talking about here in a moment. 3 is the absolute standard for call, whether that's voice or video call signaling. 4 for video, and 5 for voice traffic. And then 6 for routing, and 7's reserved. Okay, very simple with 802.1q costs. Okay, we only have 3 bits and a total of 8 values. If we're taking a look at the layer 3, type of service and DSCP bits. Now, there's a type of service field in every IPv4 packet, and we used to only use 3 of these bits and call them the type of service, or IP precedence. And since then, and this is what we're going to spend the time looking at, is we call them, or we use 6 of those 8 bits for the 1 byte, the 1 byte type of service field, and we use additional 3 bits for DSCP classifications, or differentiated services code point, as I mentioned. Okay, so first of all, we've got these bits. Well, the 1 byte, 8 bits, so 0, 1, 2, 3, 4, 5, 6, 7. These 2 are grayed out because they're reserved. Okay, so we're not going to look at those too much. These first 3 bits from left to right are the IP precedence compatible, so the older way of looking at them. And then if we look at all 6 bits from left to right, this is what we use for DSCP values. Okay, so if we were just looking, this is what I just mentioned. If we were looking at the older IP precedence, we use 3. When we're using differentiated services code point, we use 6, and these are reserved for extensions, diffserv extensions. Okay, now DSCP can be backwards compatible with IP precedence, obviously, because 3 of the bits overlap, and you'll see how these 3 bits are what we use, and we'll talk about next, for something called the class selector. Basically selecting the class, the overall generic superset class for the various traffic types. These next 3 bits with DSCP we use for what's called low latency and drop probability. Okay, low latency and drop probability. So as we're looking at this next slide that we talk about these per hop behaviors, keep in mind that these first 3 bits, and you might want to come back and reference this slide again, these first 3 bits are the class selector. They're dealing with the overall class of traffic. And the next 3 bits for DSCP are dealing with the drop probability or latency, whether it's low latency application or not. Okay, so the IET RFCs have these special keywords defined called per hop behaviors that we mentioned for specific DSCP markings. The first one is called EF, or expedited forwarding. And for the decimal value, the DSCP decimal value would be 46. But expedited forwarding, this is what we're going to use for voice only. This is specific to voice, not voice video. Next, we have the CSX, where X corresponds to the backwards compatible IP precedence value. So this is the class selector. So if I have CS1, this is going back. Let me just get my, oh, that's right, the pin won't work on here. So if I'm going back, if I'm only looking at 3 bits, and I'm just looking at those 3 bits, pretend nothing else exists, then this bit, again, pretending nothing else exists, you can't see my hand over the screen, but this bit would be the, what? That would be the 1 bit in terms of the decimal value to the binary placeholder. So this would be, or the decimal placeholder to the binary bit, if you want to call it that. So this would be the 1 bit. This would be the 2, and this would be the 4. So if I have CS1, that means that this bit is flipped on and these 2 are off. And whether that's IP precedence 1 or whether it's DSCP CS or class selector 1, okay? That's still just this bit flipped on, nothing else. So CS1 has nothing else here. If I have, let's say, CS3 or IP precedence 3, this is going to be the 1 bit flipped on and the 2 bit flipped on. 2 plus 1 is 3, so those 2 bits, it would be 0, 1, 1. That's 3, IP precedence 3, DSCP, CS3. CS3 would be those 2 bits flipped on. This is off, and those 3 are off. Now, beyond the generic CS, the class selector, the class selector are directly backwards compatible with IP precedence. Then we're also going to talk about something called assured forwarding. So assured forwarding, note that the DSCP decimal values are things like 8 for CS1, 16 for CS2, 24 for CS3. Well, you might say, wait a minute, 24. If we were looking at IP precedence 3, then the decimal value is 3, right? The binary value is 0, 1, 1, but the decimal value is 3. The 2 bit is flipped on and the 1 bit is flipped on. So how did you get 24? Well, because DSCP uses all of these bits, doesn't it? It sure does. So let's try this. Let's make this bit 0. If this bit is, I'm sorry, this bit is the 1 bit, the 2 bit, the 4 bit, the 8, the 16, and the 32. So the 16 plus the 8, what does it equal? That equals 24. So if we had 0, 1, 1, 0, 0, 0, and this is the 8 and 16 bits that are flipped on, 16 plus 8 equals 24. That's where we get CS3 has the decimal value of 24. So the decimal values between IP precedence and DSCP are different. However, that's the reason we have these per hop behaviors, so that it's easy to visually or even audibly remember. If we're talking about CS3, we're talking about the class selector 3, which is backwards compatible to IP precedence 3. Hopefully that makes sense. I hope it makes sense. If not, you might want to pause and go back and listen to that, or you know, again, a little bit more to understand that, because we're moving on to AF, assured forwarding. Now this uses the X to be the same as the IP precedence value, so the same class selectors. However, we only use 1 through 4. We don't, with the CS, we can use 1 through 7, and this is just based on the RFC. Okay, doesn't mean that we couldn't physically use them, but this is based on the RFC. So we never talk about assured forwarding 5. Why? Because that gets into IP precedence 5 is used for voice, just like layer 2 class of service 5 is used for voice traffic, media traffic. So EF gets into that 5 range. But anyway, assured forwarding 1 through 4, so that X is basically the class selector. And then Y corresponds to something called a drop preference value. And this drop preference value, with either 1, 2, or 3, with higher values denoting a higher likelihood of dropping. So AF43 has a class selector of 4, AF4, 3, but it has a drop probability of 3. So AF43, although it sounds like it's better, is actually, per the RFC, and we're just using bits to define things, it is a less desirable per hop behavior than AF41. Okay, AF4, 4 is the class selector. It's still class selector 4, but then it also has it has 3 turned on rather than 1. Okay, and just so that we are clear, so if it had AF41, let's say AF41, the AF4 is going to be equal to the class selector 4. So I've got the 1, the 2, and the 4 placeholder for IP precedence. So it's going to have this bit turned on, these two turned off, so 1, 0, 0. So it's got the AF4. And then I'm going to only use these two bits 4 and 3, for my actual drop probability. This bit 2 here is used for low latency. Okay, low latency. So if I have 1, 2, or 3, that's only using these two. So if I have 1, that's this bit, 2, that's this bit, and 3 is this bit and this bit. Okay, so everything is a subset of, when I'm looking at the drop probability, I'm only looking at the binary for these 2 bits because these are the only 2 bits that define the drop probability. This doesn't define it. It defines something called low latency. These don't define it. These define the class selector. So DSCP can be a little confusing, but it's important that you understand it and understand how to see which bits are used. So for instance, AF41 is, of these 3, this is the 4, so that bit is flipped to on. And then 41, if we're looking at the 1, the drop probability, this is the 1, this is the 2, so this bit is flipped to 1 or on. So we basically have 1, 0, 0, 0, 1, 0. So if we take all these 6 bits into consideration, and this is 2, just in terms of the overall decimal value, and that's what I mean, the consideration for the decimal value. So 1, 2, so we have a 2 flipped to on, 4, 8, 16, 32. So the 32 is on, plus the 2 is on, so that's 34. So AF41 equals the decimal value of 34. So these are our 10, 12, and 14 are AF 11, 12, and 13. AF 21, 22, and 23. AF 31, 32, and 33. And AF 41, where we got the decimal value of 34. AF 41, 42, and 43. Okay? And then BE is best effort. Decimal value of 0, this is just best effort. And here are each of the various RFCs that define these expedited forwarding or class selector, assured forwarding, or best effort. Okay, now just because something is marked with AF41 and another type of class of traffic is marked with AF43, does this mean that every router will automatically prefer AF41 over AF43? Does this mean that they will automatically drop AF43 more often than AF41 because that last 3 is the drop probability, and a higher drop probability means a higher probability of being dropped? That doesn't mean that every single router or switch will automatically do that. QoS isn't configured automatically. It's up to you and I to implement it properly. Now, could we choose, or could somebody, a service provider or someone in the cloud, could they choose to prefer AF43? Maybe even give it priority and mark expedited forwarding as drop. Yes, the answer is yes, they could. Technically, you can do whatever you want with the routers. Whether this, this is IETF RFCs. This isn't just Cisco routers. Whatever vendor of routers, they could do whatever they want. Okay, but these RFCs contained within the overall DSCP suite or package of definitions and RFCs, they provide the framework of what we should do with them and what we are, what we're given this framework to consider as what we should be doing, or if we want to follow the standard, it is what we have to do. But it doesn't mean that you have to configure. So you can configure AF43 to be the best type of traffic in your network. Okay. Again, it doesn't mean what you should do. So this isn't something that's automatic. This is something that we have to configure. Okay, so taking a look at Cisco's QoS media model. This is their baseline model based on RFC 4594. So first we're going to look on the left at the application class. The next will be the per hop behavior. Do we need call admission control? What type of queuing and or optional dropping? And then give some examples. So VoIP telephony, we mark this with the per hop behavior of EF, or expedited forwarding. Call admission control is required, and we give it not only guaranteed bandwidth in queuing, but priority, strict priority. It goes out first every time. No arguments. Regular voice calls, G711, G729, IP phones. Next, we have broadcast video. You're going to notice that we have a few different types of video. So we've got 4 different types of video here. Broadcast video, real-time interactive video, multimedia conference, and multimedia streaming. And let's jump over to the examples. So broadcast video might be IP video surveillance or Cisco Enterprise TV. Real-time interactive might be telepresence. Well, this is what they're saying. This is their recommendation. So it would be, if you're following their recommendation, telepresence. Multimedia conferencing would be unified personal communicator, where we have a video component to that. If it's just a voice only call, then it fits up with IP telephony. But if it's a video-based component, then we classify the video portion of the traffic as this multimedia conference. Multimedia streaming might be things like digital media system or video on demands. Okay, they're not as important as unified personal communicator, but then again, UPC isn't as important as telepresence, and none of those are as important as actual security. Watching video surveillance of somebody breaking into a car in a parking lot or something like that. Okay, so broadcast video surveillance is going to be given CS5. Now, you might say, well, wait a minute, I thought we just said it's only used 1 through 4. Those are the AFs. CS are used all the way up through 7. The AFs are only used 1 through 4. So call admission control is required for all 3 types of video, except when we get down to the 4th, multimedia streaming for media systems. It's recommended, but it's not required. For telepresence, we typically want to give this priority queue. Okay, so we might even have 3 priority queues. Again, each one is going to be serviced until it's empty, and then it'll move on to the next priority queue, serviced until it's empty, moved on to the next priority queue, serviced until it's empty, and then we'll get to the rest of the traffic. Whereas unified personal communicator, maybe we're not giving it the priority queue, we're just giving it guaranteed bandwidth. And at some point we have to drop traffic, so maybe we'll give it DSCP-based weighted read. So this only says AF4, which is the class selector. But we certainly know from other documents that this would probably be AF40, AF41 and AF30, 1. Okay, so the drop probability than something else. And we might not only have, first of all, we can have any number of classes that we choose. Maybe we don't have all these types of traffic. Maybe we're only going to have a 3-class model where we have VoIP, signaling for that voice, and then we've got best effort. So 3 classes, one of those being just best effort default. Okay. We might have a 4-class or a 6-class model. We might have a 12-class model. We might have a 15-class model. It just depends on our actual traffic on our network, our baseline of that traffic, and really how much bandwidth do we have available? Do we have enough to carve it up that granularly? If not, some of this won't necessarily be in this many classes, okay? But this is just an example. Then we've got network control, so SPF, EIGRP. This is at CS6. EF is only getting into the 5s, actually. CS6 is a bit higher. Now, it doesn't have priority queue, but it does have guaranteed bandwidth for EIGRP, OSPF, BGP, HSRP for hot standby, IKE, security, IKE and ESP for security. Then we've got our voice and video signaling given CS3, guaranteed bandwidth, various signaling protocols. We've got various operation, administration, and management type protocols like SNMP or SSH or syslog, things that we need to be able to get in quickly to troubleshoot. Maybe we want to classify that as CS2 and give it a guaranteed bandwidth. Regular bulk transactional data. So things like WebEx or Meeting Place or Enterprise Resourcing, maybe SAP, Oracle, those type of ERP apps. Guaranteed bandwidth, but also give it DSCP weighted read. Okay, so this weighted read is the dropping, the weighted random early detection or weighted random early discard, as I like to call it, based on the DSCP value. And by the way, the reason that they're putting only AF2 is they're just giving you the class selector, the 2. It's up to you. Maybe you've got 3 different types of transactional data, and one of them, AF21, is going to be more important that you don't drop it than AF22, a second class within that transactional data, and AF23, which is going to be more likely to be dropped. So you configure your DSCP-based dropping mechanism, your weighted random early dropping or discard, to drop AF23 faster than it drops AF22 and faster than it drops AF21. So this might represent bulk data, AF1, so 11, 12, and 13. Again, guaranteed queue and weighted read based on DSCP. Might be email, FTP, backup applications, content, all TCP-based information. And then we've got best effort, which is default, which is 0. This is default queue and read, so just random early detection. There is no way to weight them based on DSCP because the DSCP is 0. And this is all the default class, all the rest of your traffic. And then look at this, scavenger, CS1. Now wait a minute, CS1 is higher than DF, 0. So this is going to get the minimum queue possible. We're going to police it down to 8K, which is the minimum we can do. And then if it violates that, BitTorrent, Xbox Live, whatever's on your network that you don't want, or that you want to have minimal bandwidth, you give it that minimal bandwidth. But why is it marked higher than 0? Well, because if it was marked at 0, we don't know what's there. Everything else is there, and there could be hundreds of types of traffic. So we have to mark it something other than 0. But in terms of its place in the network, it's certainly less important than everything else, including my bulk best effort data. So now let's take a look at the need for congestion avoidance. TCP flows synchronize in waves, and these synchronization waves can actually waste available bandwidth. So let's take a look at an example. Here we see 3 waves, and they're becoming synchronized as they go along, right? So the problem with this is that they begin at some point ending up all of this the utilization. So here is 100% of the bandwidth, of the available bandwidth. These three flows sync up by the second interval, just a given interval. And by the third interval, all four TCP syncs have synced up. Now, why are they dropping back off? We see this tail drop occur right here, and actually at each of these three intervals. Because once they burst up, they're greedy, they burst up, they hit the top. As soon as they hit the top, the buffer is full that can't hold anymore, and so it drops the rest of the traffic. And every time it drops that, the TCP flow basically stops and has to retransmit. We receive a, wait a minute, from the other side. The other side says, wait, stop talking to me. Retransmit what you just said. So the whole TCP flow goes to the floor, and it then retransmits the last lost packet that should have been basically right here if it was continuing up beyond 100% or if there was more bandwidth. And then it bursts and it's greedy back up and everything's fine and they're talking and talking, and then all of a sudden we hit the roof again and everything comes back down. So the problem is we have all of this traffic dropping at the same time. So we've got this wave effect, like we said. We've got this wave rolling into shore. But the problem is, look at all this white space right here. If I colored these in, you wouldn't see the flows behind them, you know. But if I colored these in, you would see this is all used bandwidth right here. But up here in this white space, this is all unused bandwidth. This is wasting available bandwidth. So instead of allowing all the TCP traffic to synchronize into these waves and having these great big areas base in between the wavelength, you know, the in between the crest, what is it called, the peak and the valley, I guess, of the wave. What we can do is we can randomly, congestion avoidance randomly drops traffic, or as we talked about, based on the DSCP value, each of these flows are based on a type of traffic, a class of traffic, an application. So they've got these DSCP values. So if they've got a higher drop probability, AF33, for instance, versus maybe AF32 and versus AF31, less likely to be dropped, then maybe we say that we're going to drop AF33 3 times as much, AF32 we're going to drop twice as much, and this is just a very random example, and what we would do, I'm just giving you a general concept example. And AF31 we're going to drop, but only one time, 1-to-1. Basically, we're going to drop it, but we're going to drop AF32 twice as often and AF33 3 times as often. So every time this one gets up here, we're going to drop it 3 out of every, 10 times. And this one 2 out of every 10 times, and this one 1 out of every 10 times. So this purple line will get dropped once it hits the top, but not every single time that it hits the top. We're going to begin dropping this type of traffic first so that this one is less likely to hit the top. Why would it ever not hit the top? Well, not every type of traffic, if I send a web request, it doesn't use, if this is a switch and it's a 100 megabit fast Ethernet switch port, an HTTP request does not use 100 megabits of traffic, ever. And so it's less likely to get up to that top if other traffic is being dropped first. Now, if it finds itself contending along with all the other traffic, then all the other traffic could push one of those TCP flows up to the top of that 100 megabit buffer of a switch port. And so that's where it would have been dropped before. But if we're dropping higher drop probability, so less important traffic at a faster rate randomly, those traffic types will retransmit, but it's less important. So the ones that are more important, that are less likely to ever hit that 100% mark, are less likely to drop. So let's take a look at congestion avoidance algorithms. Okay, so queuing manages the front of the queue, which packet basically gets transmitted out onto the wire first. Congestion avoidance algorithms manage the tail end of the queue, which packet gets dropped first when the queuing buffer fills up. So weighted red can operate, like we said, in a diffserv compliant environment, and it drops packets according to their DSCP markings. And it works best with TCP-based applications. So it's important that as you're planning how you're going to mark your assured forwarding classes versus just CS, your class selector, but you're assured forwarding with their drop probability, and you're going to assign weighted red and configure that to deal with the higher drop probabilities first, then it's important to make sure that you're classifying. Back at the very first thing we talked about was classifying and marking these congestion avoidance or congestion management techniques. It's important that you're classifying and marking your traffic accordingly to how you want them to ultimately be treated. Okay, so here we've got our queue. This is the queuing at the beginning, and this is the end of the queue. So this is where tail drop or weighted random early detection, the congestion avoidance happens here, the congestion management happens up here. Okay, so here's where we have these 3, 2, and 1, and we also have 0. So 0 would be the CS, the CS1, CS2, where the drop probability bits are not marked at all. They're all set to 0. But then as soon as I go from CS1 to I want to add a drop probability, I do AF1 and I add the drop probability. Is it 1, 2, or 3? So is it AF 11, 12, or 13? Well, 13 is going to get dropped first. 12. So it's going to basically take, and the tail drop mechanism is going to look into the queue and it's going to say, oh, there's a 2-bit for the drop probability. I'm going to drop that one next. And then I'm going to drop this one next. And if these haven't, maybe these have all transmitted by this time. If I still am full, hopefully more 3s and 2s will have gotten in here. If not, then I'll drop a 1. Okay, but I'm not dropping the 0. Now, what does happen at the end of the queue? At the end of the queue, there is a tail drop. So here's where weighted red comes in and says, I've got this much of a section, and I'm going to drop, my animation wasn't great because I dropped a 0 there. I shouldn't have dropped a 0. I should have dropped a 3 and then a 1. Okay, but that's where that weighted red comes in and deals based on the markings with drop probability targets first. If I don't drop anything, if the queue fills up, there will be a tail drop. Can't help that. There's only so much memory to store so many packets. So taking a look at DSCP weighted red operation, here's where we begin dropping AF13, then 12, then 11. Okay, so we drop 13, then 12, then 11. Just another graphic to try to illustrate the same point, because weighted red and DSCP assured forwarding with the drop probability have historically been probably one of the biggest points of confusion for students of mine in QoS. Okay, so now let's take a look, move on and look at shapers versus policers. Traffic shapers versus policers, they're very similar in concept, but then in execution, upon closer inspection, they can certainly be a little bit different, and so we want to be sure that we're very clear on what the differences are. Policing, we apply at either the ingress or the egress of the device, although ingress is preferred. The thinking behind this is, if I'm going to drop something, if it violates a certain rate, why would I wait till the packet goes all the way through my router? It has to be, Cisco Express forwarded, has to deal with a routing information base. If it's not, if it's process switched, why am I going to use up the CPU of my router if basically I'm just going to drop the packet because it's beyond the rate that I'm going to allow? Okay, so that's why we typically prefer the ingress, but we can police at the egress. Whereas traffic shaping is egress only. With policing, really define profiles for policing and shaping, but anything that's out of the profile in policing, packets are typically discarded. Now they can be, as we mentioned, remarked as an alternative, but we typically drop them. With shaping, packets aren't dropped at all. They're queued until the buffer gets full. And obviously once the buffer gets full, then they're discarded with tail drop. But the idea is to queue these packets and then to allow them to build up if they're out of profile. Okay, we're shaping and molding the traffic to the utilization of the bandwidth that we want versus just being a hard policeman that says, no, if you are beyond this, you are done. Okay, policing the dropping causes retransmits, TCP retransmits. And with shaping, we're buffering these or queuing them, so this reduces TCP retransmits. Reduces UDP packets from being dropped, which can't be retransmitted. Policing, we do allow for packet remarking or marking in general instead of dropping. Shaping, marking and remarking are not supported. We simply drop when the buffer gets full. With policing, we don't use memory for the policing operation. I mean, there's some memory for the actual, daemon that's running, that's doing the policing, the process, but we're not using memory to store anything. With shaping, we're actually queuing or buffering, so we are using more memory, but it also supports frame relay congestion interaction. So this means frame relay has something that we won't probably talk too much about, maybe a little bit, called fecns and beckons. Forward, fecn is FECN, beckon is BECN, and a fecn is a notification. A beckon is a backwards explicit congestion notification. These are things that frame relay switches signal to state that there's either congestion ahead or congestion behind us. And what should we do to change our profile in order to accommodate this? And with traffic shaping, we can actually interact with that frame relay, those frame relay mechanisms. So taking a look at traffic shaping versus policers. Without traffic shaping, let's say we have, first of all, let's say maybe there's actually a physical rate to the interface that's slightly higher, but we might very well define this could be the line rate, the actual 100% of the interface, or we could define a hard policer. If we have a hard policer, it's going to get up to the top and it's going to drop. Remember, this is a little bit different than weighted red. With weighted red, random early discard, or weighted random early detection is what it's really called. We're based on those DSCP values that we just got done talking about. We are randomly dropping different types of traffic to make sure that we're trying to avoid congestion. We're trying to get into to make it so that we don't have to deal with these types of hard policers. But a policer is completely traffic agnostic. It's completely DSCP agnostic. It doesn't matter what type of traffic it is. It doesn't matter what DSCP value is there. If you go above the rate, okay, think of the policer like a policeman on the road. If you're going above 60 miles per hour or whatever the, traffic rate happens to state, well, obviously they would get through. Or if you're the Prime Minister of Malaysia, or if you're whomever, it doesn't matter. With a policer, you will be dropped if you go above the rate. Okay? So now, of course, we can make policers only active on certain classes. So in that regard, traffic only ever got into a class that had a policer if it was only based on a certain type of traffic. So in that regard, we can actually be deterministic of who is policed, who is dropped. Okay? But it's not, the policer isn't taking that DSCP value into effect as it's doing the dropping. It's simply, if you got into my class, if you got into my particular class map or section, you will be dropped if you go above this rate. Okay, whereas weighted red is police the back of the pool, the back of the bus, and drop certain bits off that are less desirable. Okay, so I understand how they could seem similar to one another, but they are really attempting to deal with two different problems. Okay, so with shapers, let's say we have a shaped rate right in here. Now remember that once packets go beyond that shaped rate, we're going to queue them in our buffers, in our memory. And then we're going to let them out on the line slowly. And what ends up happening is we end up, as traffic builds up, we end up, instead of bursting all the way up to the line rate and then dropping back down, we end up smoothing out over time. Why do we smooth out versus just being dropped like a policer does? Because we're buffering that traffic over time. Now we're going to talk about the mechanism that provides for that in a moment. It's called the token bucket. But before we do that, we just want to understand what we're trying to accomplish with traffic shaping. We're trying to use more of that previously unused bandwidth. We're trying as best we can not to drop the traffic. We're trying to instead shape that traffic into a more manageable, even higher bandwidth utilization flow. Okay. Also, something else that's very important is that, other than the fact that this is very common on NBMA, non-broadcast multiple access type network topologies, that traffic shaping is actually required on software interfaces to allow queuing to occur. Now, we talked about queuing, and I mentioned that there is a form of a queue or buffer here, but we're talking about queuing earlier. We're talking about guaranteed bandwidth or priority bandwidth, priority queuing. That form of queuing, if we don't have a hard reference point, which is the hardware queue. Now, I'm kind of getting more into routers than I am switches. With switches, we've got a lot of hardware queues, depending on whether it's a 3550 or a 3750 or a 6500 line card, and each line card has different capabilities. There could be all the way up to 8 queues, one priority queue and 7 additional queues. So depending on the hardware, depends on how many we have. But when we get into routers, we really only have one hardware queue. Whatever interface I'm leaving, that hardware queue has a transmit ring. And I'm talking about the 9 and 3900s. I'm not talking about the 7206 VXR or the 10,000, 12,000 series GSRs with distributed platforms. Okay, those get into their various distributed architectures for QoS, and the concepts are still the same, but there are obviously distributed architectures with more hardware queuing capabilities. But talking about the enterprise, let's say I have a serial interface for a T1 or maybe even a T3. I've got, or an E1 or an E3, I've got a TX ring, a transmit ring, my one basic hardware queue. Okay, and that's the reference point and the speed at which that can transfer data. So the problem is once I get into software interfaces, what do I mean by a software interface? Well, if I create a virtual template, which creates a virtual access interface, or if I create an interface tunnel, whether that's for GRE or whatever I happen to use it for, DMVPN, whether I create, maybe I create just a sub interface. So I've got a serial interface, serial 0/0/1, but I've got a sub interface .1 and .2 and .3 to carve out different PVCs. Well, those are actually, even those sub interfaces are software-based interfaces. They're not really the hardware interface itself. And queuing, you cannot put priority queuing or class-based weighted fair queuing, or the combination of the two, which is called what? I know it's been a long lecture, but it's called low latency queuing. You can't put those directly on a software interface. You have to provide a hardware point of reference, or you have to provide some point of reference comes in, and it provides that concept of the actual forwarding rate to software queuing. Okay, so we have to have traffic shaping nested as basically the base or the foundation on which we build software queuing, bandwidth, guaranteed bandwidth, or guaranteed priority queue, in order to have that queuing work if we're not placing that queuing on a hardware interface. Okay, so that's a very important bit. So taking a look at traffic shaping terminology and definitions. We've got something called shape average. This defines average traffic that should be transmitted onto the line, or the average traffic rate. We've got two things that are really for frame relay traffic, is working for CIR, I guess loosely could be defined as the shape average. But so the rest work for generic traffic shaping and frame relay traffic shaping. And then with traffic shaping, with frame relay traffic shaping, we've got min CIR and CIR. Min CIR would be the traffic maximum when priority queue traffic is present, or when there's traffic present in the priority queue. And this would basically be equal to the carrier agreed CIR speed. So typically when we have frame relay circuits, we have what are called the port speed, the full bandwidth at which we can transmit, and then we've got the CIR, what the carrier calls the CIR, the committed information rate. And what the carrier calls the CIR, maybe you've got a 512K port of CIR. If you go above the 384, you burst into that additional 128K to the 512, then you're going to end up with something called the frame relay DE bit, or the discard eligible bit, marked to 1. This is basically saying, hey, if the frame relay network experiences beckons or feckons, they experience this congestion notifications, we're going to mark anything that was above the agreed guaranteed speed. We're only guaranteeing you 384, but go up to 512 at your risk. Okay, so what Cisco calls the CIR is what the carrier would call the port speed, and can be burst up to when there's no priority queue traffic. What the carrier calls the CIR, Cisco's calling the min CIR. Okay? So probably don't have to worry too much about those unless you're still dealing with legacy frame relay networks. It'll be on the exam, although still good to know. You never know, they could ask you about them. Then we have something called B sub C. Okay, with B sub C, or committed burst, we've got the amount of data that's guaranteed to be delivered at any one time interval. We'll talk about the time interval in a moment, but the time interval is known as T sub C, or the committed time. We also have B sub E. So this is the excess burst. This is additional amount of data that can be attempted to be delivered if no congestion's present. We're going to talk a lot more about when these get used. And then T sub C, or the committed time, a regular interval, either defined or automatically calculated. Typically calculated by the token bucket theory, which is what we're about to talk about next. But we had to define these could really go in to the token bucket. So, token bucket theory. Now, this may or may not make sense to you. I hope it does. I'm going to do my best to make it make sense, or to help it make sense. But I can certainly understand if you're confused by it. Many people are. However, it wouldn't be a C-Voice class, or part of it wouldn't be a QoS class, wouldn't have the necessary information that you're going to need to understand throughout the rest of your studies and take and pass the exams if we didn't talk about the token bucket. So the token bucket is the theory behind how traffic shaping works. And it's basically this: the bucket size is B sub C, the committed burst, plus B sub E. Okay, and this is the basic single bucket. We're going to talk about single buckets and then dual buckets as well. Transmitted packet consumes a token equal to the packet size. So if I've got 100 tokens, I can transfer 100 bytes of data. If the bucket has 1,000 tokens, then I can transfer 1,000 bytes of data, or almost a meg. Okay? And we basically forward the value of B sub C, the committed burst, for every T sub C. So every time interval, whatever that time interval is, and we measure them in seconds, right? So whatever fraction of a 1 second whatever fraction of a second is the time commit, we're going to forward a burst commit, or that much data, whatever that is. Okay? And then occasionally, the committed burst tokens have built up from previous time intervals. Now the formula is this: B sub c divided by T sub c equals the CIR. Okay? And another way to put that is B sub c divided by CIR gets you the T sub c. Now we typically don't define the time interval, but let's just go ahead and assign a value to our CIR. Let's say it's 512. Okay? If this is 512, we actually define these in bits per second. So if this was 512,000, which would be 512 kilobits per second, but 512,000 is going to be, in fact, let's just take and come over here and say we've got the formula was B sub c divided by CIR equals our time interval, T sub c. So if our CIR is 512,000 and B sub c, oops, I didn't mean to write B sub c again, but our committed burst, if we define that as 5120 and we divide 5120 over 512, and I'll just bring up a calculator to show you, not that I can't do the math. So if I say 5120, 120,000, I get 0.001. What's 0.001? That's going to be, that's the 10th and that's the 100th. So that's going to be 1/100th is my T sub c. So 1/100th of a second is going to be the time at which every 1/100th of a second I'm going to put this much data out onto the actual wire, out onto the transmission wire. Okay, so 100 times in 1 second, I'm going to put 5120 bits of data, or 5.1, right? I'm sorry, not that. 5.1 kilobits, roughly 5.1 kilobits per second onto the wire. And if I do that 100 times, I'm going to equal the 512. So I'm slowly placing all the data onto the wire until it very smoothly, not quickly bursts up, but smoothly bursts up to the full shaped rate. Okay, so if I'm at 1/100th and there is, let's say, 1,000 milliseconds per second, so what does that make me in terms of milliseconds? Is that every 10 milliseconds I'm going to put this much data onto the wire? 10 times 100 is 1,000. So every 10 milliseconds, 5120 bits onto the wire. Does everyone see how I got that? Oops. Okay. So let's go back. So that's my value. And the CIR, as I mentioned, equals the shape average value if we're using generic traffic shaping. So with a single token bucket, here's the operation. If enough tokens exist when a packet enters a shaper, then the conform action is going to be applied. So this is dealing not just with shaping, but it's also dealing with policing as well. So if I'm dealing with policing, then I've got conform, exceed, and violate actions. But we don't really have these conform and exceed and violate actions. So tokens equal to a packet. So let's look at it from the perspective of the policer. So tokens equal to the packet size are used up and therefore removed from the token bucket, and therefore the packet gets transmitted. So like I said, if I have 5120 bits of data to be transmitted, then 5120 tokens will be removed. If there's not enough tokens, then the exceed, and I said shaper here, I should have said policer because we're talking about the exceed action. So if we're dealing with a shaper, we're going to buffer until enough tokens exist. If we're dealing with a policer, the drop or possibly a markdown action is going to exist. In a single token bucket, burst value defined. Okay? If we're dealing with a dual token bucket operation, anytime that you add the word violate, okay, we always have conform. If you conform to the profile that the policer is set up, obviously you conform. If you exceed that, then that's dealing with the first token bucket, and you've exceeded the amount of tokens that token bucket has. If I add a violate action, then I'm dealing with two token buckets. That is, if you overflow from the first token bucket, you're not transmitted, but you exceed that first token bucket, then you can go on to a second token bucket if there is the command violate. And the command or the, that command in iOS, second token bucket. So you can exceed the first bucket and still have a second bucket worth of grace, if you will, or mercy, to be allowed to possibly still get transmitted. You might have been marked down or something from the first bucket, but you probably weren't dropped. Okay, so the first bucket fills with B sub C bits, and the second bucket fills with B sub E bits. So the committed burst is for the first bucket, the excess burst is for the second bucket. And if enough tokens exist in the first bucket, the conform action is applied. If not enough tokens, the packet is forwarded to the second bucket with the exceed. Okay? If enough tokens exist in that second bucket, whatever the exceed action was would be applied. Otherwise, if there's not enough tokens in the second bucket, then the violate action is applied. You could mark it down DSCP. You could do whatever you want. Okay, so that's the single token bucket versus the dual token bucket operations. I'm not going to say the same thing twice, but again, if that's confusing, you might want to go back and look at both those. And you also might want to play around in iOS at the same time. Do a police, give it a value for your overall committed information rate, and then give it a value. The next value will be your committed burst, your B sub C, and the next value will be your B sub E. And put commands in there such as your conform question, your exceed question, and your violate. Remember, if I only have a conform and exceed, it's a single token bucket. If I have a conform, an exceed, and a violate command, it's a dual token bucket. Just because with complex, with capabilities comes complexity. With the ability to have granular control comes a lot of complexity. Not a dual token bucket, but there's something called a dual rate policer. So instead of having a single rate, a CIR, a committed information rate, we have a CIR and a PIR, a peak information rate. So instead of, this is still basically dealing with two buckets, but instead of them being filled by the means of B sub C and B sub E bits, the two buckets are instead basically filled by the two different rates. Okay, so these are hard rates versus bits per time interval. Okay, so we might say if you go above 384 as the CIR, then a certain action applies. You spill an action that applies first, and then we'll give you a peak kind of a burst, if you will, but a peak information rate of 760. What did I say for the CIR? 384. So maybe the peak information rate is 512 or whatever it might happen to be. But that's the dual rate policer as opposed to a single and dual token bucket dealt with by the B sub C and B sub E bits. The conform and the committed burst and the excess burst. Okay, we're going to leave shaping and policing and take a look at fragmentation. So serialization delay is the finite amount of time that is going to be required to put frames on a wire. Now, depending on the speed of your link will depend on how long it takes to serialize. Slower speed links take less time to serialize the data. For links that are less than or equal to 768K, serialization delay can be a major factor in affecting latency, overall delay, and jitter. So for these slow links, large data packets need to be fragmented and then interwoven or interleaved with smaller, more urgent voice packets. I try to explain it like this. And first of all, let's just look at the graphic. So I've got these big data packets, and then I've got these small voice packets. So imagine this is a big truck on a 2-lane highway, and there's also another big truck right beside it, and they're both using up everything. This smaller, Bugatti Veyron can't really swerve around the big data packet if both lanes are a small, slow speed link. It can't just swerve around and get past it because maybe there's just a single lane, okay? Whereas if I break up the data to the same size as the voice and I interleave them, that is, I make sure that the data gets out but also the voice, then I'm going to have that voice transmitted a lot faster, and I'm going to minimize my delay and my variance in delay, my jitter. Now, the data, first of all, we fragment to the size of the voice packets. So the voice packets never get fragmented. They never get that additional header put on for the fragmentation. Data packets that get fragmented do have an additional, not necessarily an additional header, but they have additional bytes within the header that deals with that fragmentation. So for instance, a frame relay header is fragmentation to frame relay, then it becomes an 8-byte header. And why? Well, because I need to know that this was the first packet, this was the second packet, this was the third packet, this was the fourth, and you might just realize that I did those out of order. Well, that's exactly the point. They might arrive out of order, and so I need to have the sequence number to say this one goes first, then this one goes second, then this one goes third, then this one goes fourth, or else the data won't make any sense when it's reassembled. Now, the time that it takes to fragment that data on the transmit side and the time that it takes to reassemble that data in the proper sequence or order on the receive side, that slows down the data. So while we're minimizing the delay for voice, we're actually increasing delay for data. So fragmentation is bad for data. However, if we have voice and we have slow speed links, we on the data in order to make sure that that voice is smooth and works properly. And it's also the reason that on links, which most traditional links today, I don't know, there's still plenty of people that have under 768, so I don't want to make anyone feel bad, but a lot of links are a lot higher than 768K. So as soon as we go up to a meg or anything else, anything above 768K, we do not want to do that because the amount of time that it takes to fragment that data and then reassemble it on the other side actually penalizes the data, but the voice isn't seeing any new benefit at this point. Because why? There's more lanes of highway. There's more lanes of motorway or freeway, whatever you call it. And so the data isn't using it all, and the voice just swerves right around. Again, this is for, bandwidth savings are offset by processing delay for links greater than 768. So in other words, there are still, if we do this that I'm going to talk about, IP RTP header compression, we're going to save bandwidth. And it might seem like it's really attractive because it's always going to save bandwidth. So that's great. We can stick twice as many voice calls in where we could only stick 1 times as many calls in before. But the problem is that the bandwidth savings are offset by it takes a lot of additional CPU processing to do this compression for the headers. So links that are greater than 768K actually suffer in quality. Even though we're saving bandwidth, they suffer in the quality and really the delay, not the quality of the voice, but the delay of the voice because of the additional processing it takes. It's very CPU intensive. But the idea is that an IP header, RTP is a fixed 12 bytes, and we can take, and then we have our voice payload, and we can see that it's very small compared to the rest of this. There's so much overhead or bureaucracy just to get this tiny little voice payload transmitted. So we can shrink this down. This actually should say 2 or 4 bytes. I'm not sure why that says 5. But we can shrink the IP, UDP, and RTP header down to 2 or 4 bytes. It shrinks all of that, 28 and 12, so that's 40 bytes. It shrinks it down to 2 bytes. Unless we're using something called UDP checksumming. UDP checksum, we take a hash value, to make sure, basically create a one-way thumbprint, just to make sure that by the time we get to the other side, they can look at that thumbprint, that hash value, that check packet hasn't been tampered with or hasn't been, not even a portion of it has been dropped. Its integrity is really, who it says it should be. So that's 4 bytes if we add UDP checksumming. I'm not sure why I have to correct that slide that says 5, but it's 2 bytes otherwise if we're not using checksumming. So this is about a 50% reduction in traffic for G729, only about a 20% for G711, but then again, we're typically not sending G711 over the WAN. Okay, so let's take a look at everything kind of together. A couple quick slides just to graphically illustrate this. We come in at the ingress and we do optional policing here. But after that, we do classification values that have already been set, and so we're doing policing. But we have our classifier, either a trust or NBAR or ACLs or whatever it is we're using to classify. Once we break that traffic out into classes, then we have our LLQ, our priority queue for voice traffic and optional video traffic. And then we've got our class-based weighted fair queuing for all the additional traffic for call signaling, so guaranteed bandwidth, critical data, bulk data, and then all the rest of our best effort. Okay? And so we fair queue based on weight, based on the class weight, we fair queue all this traffic. Right? And again, the queuing only takes place when there is congestion. Then we've got our traffic shaper. So we've got our shape average or our CIR or committed burst, and we're saying we're only dropping 1/100th for a 10 millisecond time, that every 10 milliseconds we're going to place traffic onto the actual line. We have, we're placing these tokens in the bucket, and we're using this shaping algorithm to slowly put traffic out onto the line so that it shapes to the proper speed and doesn't ultimately burst up and get dropped. Then we've got basically our dual FIFO. So this is part of the hardware egress interface. So our dual first in, first out. Why dual? One, because of our voice over IP, that traffic is always getting, read priority number 1. It's always going onto the ring first. The transmit ring is that hardware queue for the egress serial. Okay, here's basically another way of looking at it, but we also are including not only the layer 3 queuing subsystem, which is what we had, okay, what we had basically looked at with our priority queue and class-based weighted fair queue, which equals our low latency queuing, but we're also adding into the picture the fact that we're doing all this at the egress, and we're doing our layer 2 link-specific type mechanisms, such as fragmentation and interleave. So we'll fragment larger data packets and interleave those with our smaller voice packets before we put those onto the transmit ring. Okay, so just some graphics to help you hopefully understand a little better. Okay, we're almost done. So for the WAN edge, the best queue speed links, which are less than or equal to 768K, that's what we call a slow speed link. We have voice or video, but probably not both. Remember, video contains voice. And we're going to use somewhere between a 3 to 5 class model. For slow speed links, link fragmentation and interleaving is required, and compressed RTP headers are recommended. For medium speed links, this says voice or video, not both. I would probably not necessarily agree to that, but regardless, we're saying only about 1.5 meg or 2 meg if it's an E1, 5 class model, and here we're going to say CRTP is optional. Now remember, the processing delay will probably be greater, cause more delay than high-speed links greater than T1 or E1. Voice and or video, we're going to use somewhere between 5 to 11 classes if we have that much traffic defined. Using a QoS baseline model that we just talked about. Multiple links would require bundling or load balancing. And we even have very high-speed links, DS3, T3, E3, OC3s, OC12s, whatever. Those are obviously require newer, faster routers and distributed QoS. So looking at a simple 3-class model, we've got the best practice or recommendation is that voice or video, if you can fit it in there, uses no more than 33% of the link. And Cisco's done a lot of testing and found that even if video or voice, you certainly can do it, but the amount of degradation to the rest of your data, your best effort traffic, will severely be impacted once you go above about 33% for your voice and video for your priority queue traffic, because that priority queue is getting serviced until it's empty. So I'm not going to touch the rest of the data. I'm not even going to touch the call signaling until that priority queue is empty. If you go above 33%, you're going to severely impact the performance of the rest of the data. Call signaling should be roughly 5%, and the best effort or all of your other classes would be about the other 62%. Looking at a 4 and 12 class model, and this is the last slide, and as far as calculating the actual demos coming up. But here is a 4 class model, so that's the inner circle. We've got our real-time video, where we've got about 33%, again, so voice and video. We've got about 5% for scavenger or bulk data. We've got about 25% carved out for best effort, and the rest is guaranteed bandwidth. And in this guaranteed bandwidth would be my signaling. And then the 12 class model is the outer ring. We've got 25% best effort, 1% scavenger, 5 bulk data, 10 transactional, operations, administration, and management, 2%, signaling 2%, network control 2%, multimedia streaming 10, multimedia conference 10, real-time interactive 13, broadcast video 10, VoIP. I don't think you're going to have to remember 4-class model in terms of what percentage of bandwidth. Certainly if you remember nothing else, remember this. Voice and video should get no more than 33%, and call signaling should typically get no more than 5% of your overall link utilization.